Hi everyone. The idea of this video is to summarize everything we've done in motion so that you can study from it. So I'm going to use exactly the same approach that I used in class, focusing on graphs and areas in graphs and gradients and so on, but everything is just condensed in one video. Okay, we're going to start with the notion of displacement, and the idea is quite simple. So imagine that you're right here. This is you. And there's a little toy car right here. And you want to know how far the car is from where you're standing. Now, of course, the car could move this way. So, for example, it could move 4 meters this way. And then you say, well, the car's displacement is 4 meters because it's 4 meters away from where I am measuring the car. But what if the car did this? Oops. And over here. And it moved 4 meters the other way. Now, how could you tell the difference? It's like, well, yes, move 4 meters, but it's not the same moving here than moving here. So you need to have some way of distinguishing both. And the way we do this is by using signs. So what we say is, well, I'm going to say if the car has moved to the left, I'm going to call this minus 4 meters. And if it's moved to the right, I'm going to call this 4 meters. Now, of course, this is pretty arbitrary in the sense that you determine where 0 is. So what if you were here? Well, then this would be minus 6 meters and this would be 2 meters. And if you were here, this would be 0 and this would be minus 8. So really the displacement always depends on some point of reference that you take to be maybe where you are or where your motion sensor is or something like that. But the idea is always the same. Once you choose your point of reference and you say, okay, this is 0, then displacements to the left are negative and the displacements to the right are positive. And this way you can know whether something is moving to the left or to the right. Okay, now imagine that I have my car, and my car is actually moving. So it's moving this way. And of course it could be moving like this, but I think it's just easier to represent it this way. So let's just say that you're here, and then your car starts right here when you have a timer. Right? So you start your timer, and then your timer is set at 0, the car is right here, and then after 1 second the car is here, and then after 2 seconds the car is here, 3 seconds the car is here, and so on and so on and so on and so on. So that the car moves the same amount of distance every second. And I would like to plot this thing. Now, when something moves the same amount of distance every second, we say that its speed is constant. So basically we have a car that's going at a constant speed. So if I want to plot this, all I need to do is be like, okay, well, at what time was the car where, right? So here I will put the displacement of the car, and here I will put the time. And basically this is just as easy as taking the car and moving it, and just like it moves like this, so it would be doing this thing, but as the time goes by, I need to also shift it this way. So basically what I'm going to get is a movement that goes like this. And you can see what kind of graph I'm going to get. Another way of looking at this is saying, okay, well, let's just say that my car moves 2 meters every second. So after 1 second, it's here at 2 meters. Okay, so I can just go here and make a bunch of 2, 3, 4, 5. So this is 5 seconds. This would be 10 seconds. This would be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So after 1 second, it's at 2 meters. After 2 seconds, then it will be at 4 meters. After 3 seconds, it's going to be at 6 meters. And you can easily see that this is going to make a straight line. Well, that was trying to be a straight line. Of course, I'm not very good at drawing straight lines. That goes up this way. So this means that my car is going to be moving this way. And if I plot this in space, like in the displacement time graph, oops. Well, that wasn't supposed to have happened. The car will do something like this, right? Okay. Now, the next question I would like to ask myself is what happens then if instead of starting the car right here, I started the car right here. So what if when I started my timer, my car wasn't right next to me, but it was maybe already 4 meters away? But if he started 4 meters away when I started my timer, it means that at t equals 0, means that when my timer said 0.000, my car was here. And then after that, it was at 6 meters. And then after that, it was at 8 meters. And so on. And then you can see that I get another straight line, which is parallel to this one, but a little bit further up. So all that changes if I change my initial displacement, so the initial position of my car, is that the graph becomes a little bit further up or a little bit further down. But if the speed is the same, you see, the two lines are exactly parallel, which means that the gradient, which means the slope of the line, how steep the line is exactly the same. Now before I tell you, I would like you to think about what do you think is going to happen if the car goes a little slower? What will happen to this line? So imagine that I start my car at 0, 0, but instead of doing 2 meters every second, it just does 1 meter every second. Is the line going to be just as steep, steeper, or less steep? Well, here all we can do is just try it, right? So if it does now 1 meter per second, we say after 1 second it's done 1 meter, after 2 seconds it's done 2 meters, after 3 seconds it's done 3 meters, after 4 seconds 4 meters, and so on. And you can see that what I get is a line that is less steep. Conversely, if the car had been going faster, I would get a line that is more steep. So basically what we see is that the faster my car goes, then the steeper the line gets. Okay, so far we've seen what happens when I have my car, and then my car is going forward this way. But what happens if my car is going the other way around? So instead of starting at 0, for example, it starts at 10 meters. Remember that I'm here. And then my car starts moving back until it reaches 0, and then it keeps going down. So first thing, how can we represent this? Well, one thing that I can do is, let's just say that I start at 10 meters. So again, let's just make a couple of 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Here, same thing. 5, 1, 2, 3, 4, 5. So let's say that the guy starts here at 10 meters at second 0, and then it moves again 2 meters per second. Well, it starts here, but after 1 second, it's now at 8 meters because it's moving 2 meters per second. So 10 meters, then 8 meters, then 6 meters, then 4 meters, and so on, right? So if I put it here, this would be like 10, 8, 6, 4, 2, 1. So you can see that what I'm going to get is a line like this. So after 1 second, 8 meters, 6 meters, 4 meters, and so on, and then you get a line that goes like that. So see, when the car was moving forward, the line was going up, but now that the car is moving backwards, the line is going down. And now we have a problem that's very, very similar to the one that we had before, when we had a guy and we didn't know. So like if my car is here, for example, I say my displacement is 4 meters, but what if it's here? Then how do I distinguish between these 4 meters and these 4 meters? Well, I have to add a negative sign. So how do I distinguish between a speed that goes forward and a speed that goes backwards? Because it's not the same to say, oh, here's a truck going at 100 kilometers away from you, than here's a truck going at 100 kilometers per hour towards you. In the second case, you should be a lot more worried because you're about to be run over by a truck. So we need to find some way of distinguishing how the car is moving. And we're going to do the same thing that we did for displacement. So if the car is moving this way, up, or for example to the right, we're going to say that the speed is positive. And if the car is moving backwards or to the left, we're going to say that the speed is negative. But because this is not quite a speed, it really doesn't matter to say that the speed of something is -2. It just sounds a little weird. We're going to change the name, and we're going to call this thing velocity. So velocity is sort of like a speed. It tells me how fast something it is, but I also can use the sign to know whether it's moving to the right or to the left. That's pretty much it. So for example, a velocity of -3 meters per second means that the car is moving at 3 meters per second, but to the left. Or alternative, it's moving up. So either to the left or up, depending on whether it's moving up or down or to the left and right. Now, how does this translate to the graphs? Well, as you can see, now my slope, my line is going down instead of going up. So my slope has changed. Before, I had a positive slope, the gradient of my graph was positive, and the faster that I went, the bigger the gradient got. And in this case, I have the opposite, right? I have a gradient that's negative. Then that's what's telling me, hey, this guy is going backwards. It started at 10 and now it's going towards 0. Again, the less steep this guy is, then the smaller the velocity will be. The steeper it is, the greater the velocity will be, of course, with the negative sign. Now, how can I calculate the velocity? And this is the most important point we're going to make today. Well, we saw that the velocity is related to the gradient. In fact, I'm going to start a new slide and show you in a new graph. Okay, so imagine that I have this movement here. So this is a car that starts around here and then it's moving up. So that if we have the graph, it goes a little bit like this. And I would like to know how fast it goes. Well, if I want to know how fast it goes, I need to know how many meters does it go through every second. Now, one way that I can do this is just simply go and say, okay, well, after 2 seconds, for example, how many meters did he move? Well, let's see. So these are 2 seconds. So 1, 2. So, and I just make a little line up, see where it intersects my line. And then I can use this point here to see how much he moved. So as you can see, it moved up to this point here. Now you might think, oh, it moved 3 meters, right? 1, 2, 3. But it didn't, because it started at 2 already. So really what it moved was from 2 to 3. So in 2 seconds, it moved 1 meter. So if in 2 seconds it moved 1 meter, how many meters per second did it go? Well, the speed then would be, it did 1 meter in 2 seconds. So that's just 0.5 meters every second. And this is just common sense, really. Now, if you realize, this number that I just calculated is something that in mathematics we call the gradient. See, I looked at how much this rised, and I divided it by how much this runs. And this rise over run thing, we call it the gradient. I could do this with any other 2 points. So for example, I could go say, okay, how much did the guy move in 5 seconds? And if I've done things correctly, he should have moved around 2.5 meters. So let me see. And I make this point here, and indeed. So this space here is 2.5 meters. This here is 5. So the speed would be 2.5 over 5, which is equal to 0.5 meters per second. So basically, if I calculate the gradient of this line, which remember tells me how steep it is, it will tell me the speed. And this is something that you need to remember. This is the one thing you need to remember. So let me just write it here. I'm just going to leave this here so that you can see it. The velocity, not the speed, but the velocity, because remember this also works if the guy is moving backward, is the gradient of the displacement time graph. If you don't know how to calculate a gradient, then that's very bad news. You need to come to see me straight away. Now, another possibility is, what if I want to know not really where my car is at each point, but how fast it is going every second? So, you know, in my car, normally I have this little thing here with a little needle, right? And the needle points at the speed of my car. And if this car goes faster, then the needle goes this way. If the car goes slower, then the needle goes this way, right? And maybe I would like to plot the position of this needle at its moment in time. And this is very interesting because it allows me to know whether my car is getting faster or is it getting slower, is it braking, what is it doing? Now to do this, it's very simple. We just need, again, 2 axes. One is going to be the time, and the other one is going to be the velocity. Now, in the case of the cars that we've considered so far, we had a car that was always going at the same speed. So, for example, 2 meters per second. So, okay, I just make a bunch of lines here. So, 1, 2, 3, 4, 5, 2, 1, 2, 3, 4, 5. and I would like to plot this. Well, all I need to do is just go second by second and ask myself, how fast is my car going? So at the very beginning, when my timer hasn't started yet, it's at 0, 0, 0. How fast is my car going? Well, if it's going at a constant speed, it's going at 2 meters per second. Okay. And what about in 1 second later? Well, still at 2 meters per second, because the whole point is that it's going at a constant speed. What about 5 seconds later? Well, still at 2 meters per second. So if I have to plot this, I'm going to get a perfectly straight line. So basically, the velocity time graph of a car going at a constant speed is a straight line. Now, what would happen if the guy was going backwards at a constant speed? Well, what would happen is that then the velocity would be negative, so then I would have a straight line over here. Now, the cool thing about this is that I can use speed time graphs to calculate how much my car has moved. How? Well, pretty simple. If this is telling me that it's moving 2 meters every second. So after 1 second, it's moved 2 meters. And after 2 seconds, then it's moved 4 meters. After 3, it's moved 6 meters, and so on and so on. So really what I'm doing is I'm multiplying this thing here, the amount of time, times the velocity. So let's just say that I want to know how much my car moved after 4 seconds. Okay, well, 4 seconds, 2 meters every second, that's 4 times 2, that's 8, which is just the area under the line. So basically I can use a speed time graph to calculate the displacement of my car simply by taking the area under the line that shows the velocity. And again, this is one of the 2 things that you need to know very well, and if you know these 2 rules, you really can't go wrong. So displacement is the area under the velocity time graph. Now, so far we've only considered motion where the car is always going at the same speed. But what happens if I have a car, for example, that is accelerating? So that it starts, for example, still, and it just goes faster and faster and faster and faster and faster. In fact, we're only concerned with cars that are always increasing their speed by the same amount. So for example, after 1 second, they're going at 2 meters per second. After 2 seconds, they're going at 4, and then at 6, and then at 8. So that they go faster and faster and faster, but always by the same amount. So how would I plot this in a graph? Well, let's just start with the car that I have that starts from being completely still. So at the beginning, its velocity is 0. So first thing I'm going to make some lines here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. And then here, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so let's just say that my car starts from rest, which means that it's completely still. So it's right here. When my timer hasn't started, so the timer says 0, 0, 0, my car is here. Okay, and let's say that every second it goes 2 meters per second faster. So it goes 2 meters per second faster every second. Now I could say it goes 2 meters per second faster every second. 2 meters per second per second. Sometimes in physics we don't want to write 2 meters per second because we're lazy, so we just write 2 meters per second squared because I have a second multiplying another second, so I get 2 meters per second squared. But all this means is 2 meters per second per second. Okay, so I have my car here at 0, and after 1 second he's going at 2 meters per second. Okay, so 2 meters per second after 1 second, and then after 2 seconds it's going at 4. And after 3 seconds, 6. And I guess you can see after 4, 8. I guess you can start to see that this again makes a straight line. And but this is a very different graph from before, because this is not a speed time, a displacement time graph. This is not telling me about where the car is. This is telling me about how fast the car is going. And we have a car that is going faster and faster and faster and faster. Okay. Now again, what happens if my car, instead of having started from rest, had started already at 3 meters per second? Well, if he had started at 3 meters per second, that would be its speed at the beginning. Then after 1 second, he would be going at 5 meters per second because it's 2 more, and then at 7, and then at 9, and so on. And I would have another straight line that would be parallel to the first one, so it would have exactly the same gradient. Now the first thing that I can ask myself is, okay, how many meters per second faster does this guy go every second? Well, I already told you it goes faster, 2 meters per second faster every second. And this thing has a name, and it's called acceleration. So the acceleration of this car is 2 meters per second squared, because it goes 2 meters per second faster every second. Another way to see this is that the acceleration is the rate of increase of my velocity. How fast is my velocity increasing? Well, my velocity is increasing 2 meters per second every second. Now another thing that you can see then is that these two cars that started from different speeds have exactly the same acceleration, because their speeds are increasing by the same amount every time. And if they have the same acceleration, again, the gradient of the graphs is exactly the same. And this gives me an idea that just like velocity is the gradient of the displacement time graph, so is acceleration the gradient of the velocity time graph. And we can write this down here, and again, you need to know this by heart. Acceleration is the gradient of the velocity time graph, because the gradient tells me the rate of increase of the velocity. It really tells me how many meters per second faster is my car going every second. Now, can I have something that has deceleration? Well, I certainly can. So for example, I could have a car that starts going at 8 meters per second, and let's just say that its velocity decreases by 1 every second. Well, after 1 second, then it's only going at 7, then after 2 is only going at 6, and so on and so on. So I could see 1, 7, 2, 6, 3, 5. And you can easily see that then I get a straight line that is pointing down like this. And indeed, this is also accelerated motion, but the acceleration in this case is negative, because the speed is decreasing every time. Just like velocity could be positive or negative, and it tells me whether the displacement is increasing or decreasing, the acceleration can also be positive or negative, and if the acceleration is negative, we call it sometimes deceleration, and it just means that my speed is decreasing, so my car is slowing down. So if I start at 8 meters per second and my acceleration is negative, I will go slower and slower and slower until I reach 0, and then I might start going faster and faster and faster backwards, but we will get into that later. Okay, so we're going to finish this video simply with an example so that you can see the sort of question that somebody might ask you to do. Now, let's just say that I have this graph and they're asking me to find both the acceleration and the displacement of this car. How could I do this? Well, first thing I'm going to find the acceleration, and remember the acceleration is the gradient of the velocity time graph. Okay, well, then I need to find the rise over the run. So I take any triangle. I'm going to take this triangle because it's just easy to use. But I could take any triangle and it will always work. Okay, so then I say, what's the rise? Well, the rise goes from 2 to 5. So from 2 to 5, that's a rise of 3. So rise is 3 meters per second. And how much is the run? Well, the run goes from 0 to 6 seconds. So the run is 6 seconds, sorry. Okay, so what's the acceleration? What is 3 over 6? That's 0.5 meters per second squared. 0.5 meters per second squared. So that's it. The acceleration is 0.5 meters per second squared, which is the gradient of this graph. That's the easy part. What if they now ask me, okay, how far did this car get after 5 seconds? This is a little bit harder. Actually, let's say after 6 seconds, since we're already here. Now, remember that the displacement is the area under the velocity time graph. So what I need to do is I need to consider the area under the graph, which is not only this area here, but the whole area until I reach this line. So this rectangle here and this triangle here. Okay, so how do I do this? Well, first thing I'm going to calculate the area of the rectangle. This is a height of 2 and a base of 6. So the area of the rectangle is just 2 times 6, which equals 12 meters. And now I need to consider the area of this triangle here. Now the height is 3 and this is 6, but because it's a triangle I need to divide by 2 because it's half the area of the rectangle. So the triangle is just 3 times 6 over 2, which is equal to 9 meters. So what is the total displacement of this car? Well, it's the total area, so it's the rectangle plus the triangle. So this plus this. So the total displacement of my car is 21 meters. One final thing, which is, what if I want not a velocity time graph for my accelerated motion, but a displacement time graph? Now, I'm not going to actually calculate this, I'm just going to give you a very rough way of understanding. So remember that if I had a car that was going at a constant speed, my displacement time graph would be something like this, a straight line. But now what I have is that I have a car that is going faster and faster. So maybe the first second it goes this fast, but then later on it goes even faster. So instead of doing the same amount of distance, it's going to do more. And then the next one is going to be even faster, so it's going to do even more distance, and so on and so on. So instead of having a straight line, I'm going to have a curve. So it was going to look something like this, because it's going faster and faster and faster, so each second it does more and more and more distance. So this is the typical displacement time graph of something that is accelerating. What if it's decelerating? Well, instead of going in a straight line, again, it's going to be doing less and less and less distance every time. So I'm also going to have a curve, but actually it's going to look like this. As you can see, as time goes by, this gradient keeps decreasing and decreasing and decreasing, and remember that the gradient is the speed. So the speed is also decreasing. In this case, the gradient is increasing, increasing, and so is the speed, because the speed is the gradient. Remember, the steeper the line is, the faster that the thing is moving. So this is how I can easily recognize motion that is not at constant speed when I see a graph. When I see a curved line, I'm like, oh, this guy is accelerating. When I see a curve like this, I'm like, oh, this guy is decelerating, because the gradient is constantly changing. One last thing, what if I see a line like this in a displacement time graph? What does this mean? Well, here I have someone who is, let's say, at 3 meters at the beginning, and after 1 second is still at 3 meters, and after 5 seconds still at 3 meters, and after 10 seconds is still at 3 meters. Well, this is something that is completely still. So when I have a straight horizontal line, this means that the car is still. So let's just recap. Still car, car moving at a constant speed, car accelerating, and car decelerating. And I think with this you have enough. All of these things we should have done in class, so this is just a review, but you need to know for sure really well that the velocity is the gradient of the displacement time graph, that the acceleration is the gradient of the velocity time graph, and that the displacement is the area under the velocity time graph. If you know these three things by heart, there is no way that you can do badly in any of the tests.